For our ES3C2 group design project, we developed a left-rear suspension assembly for a high-performance motorsport application. Our primary design focus was to reduce unsprung mass so as to reduce inertial effects, improving the responsiveness of the system to improve driver feel and ride quality. Key components in the suspension include the wishbones, upright, hub, bearing, CV joints, braking components, and wheel assembly. Throughout the design process, various calculations and engineering standards were considered to optimize design features. 3 configurations of components were considered for our suspension system, each offering their own advantages and disadvantages. While configurations 1 and 3 were optimized for specific advantages, configuration 2 offered a balance between ease of serviceability, component cooling capabilities, and additional unsprung mass. This design was chosen to move forward with. Initial cross-section drawings were completed to visualize relative positioning of components. For our wheel rim, we opted to use a modular 3-piece configuration, where a magnesium alloy was chosen as the material due to its high damping and high thermal conductivity properties. The rim features a drop-center design for tire mounting, as well as a silicone sealing rim to ensure that design is airtight. The wheel hub is a central load-bearing spine. Using von Mises' criterion, we identified a worst-case equivalent stress of 80.15 megapascals, which rose to 203.19 megapascals, after applying a stress concentration factor of 2.5 and a 1.3 safety factor. Several designs were considered for the brake disc, where a floating design was ultimately chosen due to its ability to utilize the properties of 2 different materials. Carbon steel was chosen for the carrier in the disc due to its high strength, and cast iron chosen for the outer disc for its ability to dissipate heat. The tapered rollers provided a 48mm apex distance and a static capacity of 163 kilonewtons, ensuring high moment resistance and an L10 life of 2.7 billion revolutions. The upright underwent several significant evolutions, where our initial design A was 5.5 kilograms. By employing topology optimization, we identified the primary load paths between the wishbone pickups and the bearing housing. Unnecessary material was eliminated to create a truss-like structure, reducing the mass to just 1.99 kilograms, a 63.7% reduction. The part is CNC machined from an aluminium alloy, which was chosen for its high strength-to-weight ratio. An M6 housing tolerance was used for the bearing seats to ensure a controlled interference fit, preventing bearing creep during high G maneuvers. Torque is transmitted from the CVJ to the hub via an AISI 4142 steel CV joint adapter. Extensive calculations were performed to ensure that the required torque is successfully transferred. Stainless steel dowel pins were selected for their high shear strength and fatigue resistance, providing the capacity to withstand the required 475 Nm of torque without deformation. The final element of our suspension configuration was a double wishbone system. Both push and pull rod configurations were considered, with the push rod preferred for its superior ease of servicing. Comprehensive failure mode analysis was completed to determine required material properties, cross-sectional dimensions, and bolt sizes. Ultimately, an aluminium alloy was chosen for the wishbone members, while low alloy steel was selected for the chassis brackets, secured with M6 bolts. Welding was utilized as the optimal joining technique to ensure a robust connection to the chassis. We were able to produce a suspension system that is analytically safe, manufacturable, and optimized for racing purposes.